Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to talk about approximating the area under a curve, which is the basis for integral calculus. So the basis of integral calculus is attempting to find the area under a curve. If we have simple shapes like these, that's not difficult. We have formula. But if that was all it was, we wouldn't need to invent a new form of math in order to do that. What we're looking at is how do we do that when we're talking about curves? And for that, we're going to need to use approximation. So when we want to approximate the area of a curve, we're going to want to break it up into pieces that we can then use those areas and add them up just like we would do a decomposition. So for example, this is a trapezoid, and we know the area of a trapezoid. But we can also break up a trapezoid into, for example, a triangle, a rectangle, and a triangle. So when we're doing this with a curve, we can't break it up into these nice, easy shapes. But what we can do is break it up into a series of rectangles. And in order to do this in a way that's useful, we use something called partitioning. So in order to do a partition, we take the interval of the curve that we care about, and we break it up into a set of partitions that are subintervals all of the same size that add up to be the interval that we care about. So for example, if I take this interval from 0 to 4 and I break it up into 4 partitions, each of those partitions is 1 unit. If I were to break it up into 6 partitions, each of those partitions would be 4 over 6 units. And the thing we have to care about here is that 1, it is a closed interval, and each of the subpartitions is also a closed interval. So they're going to share a point here, but you'll notice that we have the left end partitions and the right end partitions. And the reason that we can do that is because it doesn't matter that they share this same point on these closed intervals. Normally that would be a problem, right? Because we can't have something where a point exists in both intervals. But because we're only going to be counting it either from the left side or the right side, it actually doesn't matter that that point exists in both intervals. Because we're either going to be looking at everything from the left, so we count here, 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 and here, or we count everything from the right. So we would count here, 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 and here. And what you'll notice is that both of these are just approximations. They either have extra bits like this, or they're missing bits like this. And then what we do is we then take the limit of these as we increase the number of partitions. And when we increase the number of partitions, our approximation becomes a better approximation of the area under the curve, just like we did when we used limits for the derivative. So let's take a look at what this would look like with an actual curve using an actual idea for doing these limits. So it can often be a little bit difficult to explain this kind of in a generic sense, but when you actually just kind of apply it, it helps show what's going on here. So the formal definition of the partition is exactly what we were talking about. Effectively, we just take some interval a, b, and we let x naught be the a, and we let x in be the b. And then the partition is just however many pieces we want to break it up into. And then we just say that we're going to break it up into an even number of those partitions. And the reason it's important that we break it up this way is because what we want to do is we want to then sum up those areas. And just like in the kind of overview demonstration, we either want to sum it up from the left or from the right. And the difference in this sum is that we're either going to use these partitions using the left-hand side of these partitions, so the x0, the x1, the x2, up to the x of n minus 1, or we're going to use the right-hand side, so the x1, the x2, the x3. And we are going to be doing actual calculations here. So for these, we are going to know exactly what our n is going to be. We're going to select a number that we're going to use for this approximation. Our example problem here, we are going to be estimating the area under cosine of x. That's our f of x. We're going to be using the interval 0 to pi over 2 with an n of 4. So we're going to be breaking it up into 4 partitions. Now, the delta x, we simply take pi over 2 minus 0 and then divide by 4. And that'll tell us the size of each of our partitions. So in this situation, that's going to be pi over 8. So that means that our x0 is going to be 0, our x1 is going to be pi over 8, and then our x2 is going to be 2 pi over 8 or pi over 4, and so on and so forth. Okay? And so the goal here is compare the left-hand approximation and the right-hand approximation. See how different they are, or if they're different. Sometimes they're not if we have a symmetric graph. So try this on your own, and I'll show you what it looks like in 3, 2, 1. So here you go. Effectively, what we did was we found our x0, x1, x2, x3, and then of course the x1, x2, x3, and x4 based on our partition. And then we simply plugged those in for our cosine values, summed those up just like it says to do with our summation, and we got here that our total was 1.18, and over here our total was simply 0.79. Seems to be a pretty big discrepancy, but we also only used 4 partitions. If we were to increase this number, we would see these two numbers get closer together. And this should also make sense because when you think about the graph of cosine, it starts at 1 and drops to 0, so the right-hand sum would be lower than the left-hand sum. Now, in addition to increasing the number of partitions, we could also change where we're taking our estimation point or our sample point. Instead of taking it only from the left or only from the right, we could do something like take it from the middle, for example. And in fact, there is a different way to do this aside from just doing the left-hand sum or the right-hand sum, and we call that the Riemann sum. We'll look at that next. So instead of just using the left-hand sum or the right-hand sum, we can also do something called the Riemann sum. And that's where we use the same partition idea, but instead of using the endpoints of the partition, we use x star, which is any point on the partition, which could also be the endpoints. In fact, if we use the maximum Riemann sum or the minimum Riemann sum, that exactly approximates the right-hand or the left-hand sum anyways. So a common example of this would be using the midpoint, because that's a little bit like averaging the left-hand and the right-hand sum, which tends to give us a decent approximation. So we're going to go ahead and try that here. Let's go ahead and use the same exact function we did last time, cosine x, on the exact same interval with the exact same number of partitions. Although this time, instead of using the left hand or the right hand, we'll use the midpoint. And to find that midpoint, simply take the endpoints of your intervals and divide by 2. I'll show you how it's done in 3, 2, 1. So, as you can see, we use the same partitions. We found that our x stars were going to be pi over 16, 3 pi over 16, 5 pi over 16, and 7 pi over 16. Plugging that into our summation, we got that our answer was about 1.01. Now, what we'll find later is that the actual answer to this is 1. So that's actually really, really close. So the last thing we're going to look at here is how this becomes the actual integral for calculus. And the way this works is we simply do exactly what we did when we were looking at the derivative. And we take this idea and we go, well, what if we let the number of partitions here, this n, approach infinity? What if we said that we were going to do an infinite number, so that we were taking the area at every single point along this curve? So we're going to write that out, but we're not going to look at exactly how to do that until the next video. And here it is. If we were looking for the actual area, this would have to be the limit we would solve. And we're going to see how we can do that in the next video. For now, I'm going to leave you a couple of exercises so you can practice just working with finding the approximation using the left, the right, and the Riemann sums. So I hope you found this introduction to Riemann sums and the approximation of areas helpful. If you have any questions, you can always drop into the comments or join us on Discord. And as usual, the answers to the exercises will be after the outro.